Hello, astronomy students. This is Mr. Stockbridge. I want to give you a quick tour and a little bit of an explanation on some things in the Martian Landscapes Lab. There are a couple of things that give people a hard time every semester, and so finally, I'm trying to put together a video that'll take you through some of the biggest hurdles. Now, as I walk through things, you'll see it on your screen here, and it's not going to be perfect, but that's okay. I'm going to leave things open large screen instead of going through the actual PowerPoint as a presentation. And I'm going to do a lot of work with the National Geographic map of Mars rather than with Google Mars, just because that's easier for me to handle right now since this is just kind of an emergency lab recording. So enough of that. Let me take you through some basics here. So we're looking at the Martian Landscapes Lab, and let me get over there. First thing you need to know is this is really a geology lab. The same principles that we see in geology here on Earth largely apply pretty much everywhere else in the solar system, especially with what we're talking about today is the terrestrial planets. Mercury, Venus, Earth, Mars, and even the moons throughout the solar system all are going to experience these same types of things. So we're studying these in other places in the solar system, but this has been thoroughly studied with examples here on Earth. We're not going to see those examples, but just know that they are there. And if you ever take a geology class, you're going to see them and they'll make a lot of sense. So the two principles that we're focusing on today are the principle or the law of superposition and the law of cross-cutting relationships. The intro on the lab really focuses on superposition, but really, when you get down to it, the lab is a lot about cross-cutting relationships. We're going to briefly go through both of those. Superposition is a very, very simple concept. Basically, the oldest layers are on the bottom of the pile, but this only applies to undisturbed settings. Now, on Mars, we've not had plate tectonics in a long time, if ever. Here on Earth, as the tectonic plates move around and shift, landscapes get all kind of jumbled, rocks get folded over, and so this law doesn't apply all the time. This basically deals with simple situations where we know that tectonics has not come in and scrambled things up, so to speak. But as you see right here, the younger layers on top, and by implication, all the older things are down below. So the deeper you go, the older you get. Cross-cutting relationships goes hand in hand, but is a bit different. Basically, a feature which cuts across another feature has to be younger than the thing it cut across. Let's take a look at that in the diagram here. So obviously 1 is the oldest because it's on the bottom, followed by 2 and 3. Now, 4 has to be younger than these other layers because it disturbs them. It cuts across them. 1, 2, and 3 are not going to form around something like this, except in a few extremely unusual circumstances, and those are for a geology class, but it's extremely rare for a landscape to form around a disturbance like number 4 would be. But here we see 5 is the youngest because it cuts across number 4 by implication. We're going to see that a lot, and you're going to use that principle a lot in this lab. Now, this can be simple, as you see in the diagram here, or there are more complex situations, but these same two things help us to unravel a lot of these scenarios. So even as something as complicated as this monster here can be figured out with these two laws. Now again, this is not a proper geology class. You should take one. Geology is great, but not right here. This diagram would make complete sense to someone who's gone through a geology class. Now let's take a look at the situation on Mars. On Mars, the landscape has been shaped for the most part by just 2 different processes. Meteor impacts, which result in rough terrain. You guys know what that looks like. And then lava flows smooth things out. They recoat the surface, if you will. In a lot of ways, you're going to see things that will remind you of our lab on lunar geology, and that's because the moon and Mars are both terrestrial bodies. Okay, the moon is not a planet, but it's rocky, just like Mars is, and so the same processes will take place there. So, cratering on Mars, trying to keep my screen time down here. Basic principle of interpretation when it comes to terrestrial landscapes is the concentration of craters. In theory, early in the solar system is when the biggest pieces of debris were still floating around the solar system. Over time, these big pieces collided with other planets, both terrestrial and Jovian. So Jupiter had its fair share of impacts, but those were erased because of its atmosphere. And after a while, all the big pieces of junk were gone because they'd all been absorbed by other planets or the sun or gotten kicked out of the solar system. And so over time, we see fewer and fewer large bodies around and more small bodies. And so the large bodies must be primarily from early in the history of the solar system. All right, I've got to move fast here. Large craters tend to be older than smaller craters for the reasons we just talked about. Areas with lots of craters, Mr. Stockbridge's typos, are older because they've been around long enough that they've been beaten up a lot. Younger surfaces haven't been around, they just haven't had as much time to take a beating as the older ones. The only way to create a new landscape is not through the things you see on Earth, erosion and so forth. We don't see that. The only way to really do it is for lava to come and completely recoat a region. We're going to see that in just a second. So here we're going to largely focus on how old one part of Mars is compared to another part, and let's just kind of get to those examples. Now, quick bit of emphasis right here. We don't know how many years old these features are. We just know that this one is older than this one. Let's take a quick look here. All right, so here is Mars. This is the National Geographic poster. Now, you're going to do a lot of work with coordinates in here, so I'm going to zoom in a little bit. The resolution should be better on your screen than it is on my screen. The coordinates for longitude are along the top over here. So here's 0 degrees, 30, 60, 90, 120, 150, 180. And the same going to the right. And then if you scroll over along the edge over here, these are your latitude lines. These will help you navigate around the map a little bit. Most of this lab focuses on, well, the questions focus on things in the southern hemisphere. So I'm going to give you a few examples of things in the northern hemisphere, just very briefly. So, for example, we can just look at Mars in the northern hemisphere and know that there are certain areas that have to be young and certain areas that are definitely a bit older. The heavily cratered area here around Arabia Terra, I don't know if you probably can't see my mouse, but Arabia Terra here in the middle has got a lot of older landscape because it's beaten up. Yep, there we go. Lots of craters, fairly close together, and that's how we know it's older compared to things out here. You zoom out here a little bit more, scroll over. See out here in the plains, very few craters, very far apart, mostly smooth terrain. Therefore, Utopia Planitia has got to be a younger landscape than Arabia Terra over here. Okay, last thing, and then I'm going to end the video and let you ladies and gentlemen get to work, is cross-cutting relationships. Whenever one landscape feature interrupts another one, the interrupting feature is the older one. And I'm going to give you just a quick example. Where did I see it here? If I can find my, oh, nope, not there. Right here. Take a look at those two craters. You've got a large one on the left and you've got a smaller one on the right. How would we interpret these? Which one is older? Well, for one thing, larger craters tend to be older, but also you just need to look at which feature cuts across the other one. See this crater here on the right interrupts the ring of the larger crater. So here it's nice and big and round, but this one seems to have been placed on top of it, or we could say that the rim of this crater cuts across the border of the larger crater. That's the basic idea of cross-cutting relationships. All right, with that, hopefully you've got the basics that you need to know in order to make your way through this Landscape of Mars lab. Please let me know if you have questions, and I'll be happy to help you guys. Do your best, and we'll see you later.